Tonight we'll explore something that shouldn't exist, temperatures below absolute zero, where the very foundation of physics seems to turn inside out. For centuries, scientists believed that absolute zero, at minus 239 degrees Celsius, represented the coldest possible temperature, the point where all atomic motion simply stops. Yet in laboratory conditions, researchers have achieved something extraordinary. Negative absolute temperatures, where matter behaves in ways that challenge our deepest understanding of energy and entropy. These aren't just colder places, they're entirely different states of being, where heat flows backward and the normal rules of thermodynamics quietly dissolve. We'll journey through the careful science behind these impossible temperatures, exploring quantum mechanics, energy distributions, and the strange mathematics that make the impossible possible. If this gentle exploration of physics' hidden mysteries helps you drift towards sleep or sparks quiet, curiosity, your soft subscribe, and thoughtful engagement mean more than you know. Let's begin this slow descent into the fascinating realm below absolute zero, where science meets the impossible. Hello there, and welcome to Science for Sleep, where tonight we embark on a gentle journey into one of physics' most bewildering mysteries, exploring temperatures that exist below what should be the coldest point in our universe. Have you ever wondered what happens when scientists push beyond the absolute limits of cold itself? Perhaps you are settling in somewhere comfortably warm this evening, maybe wrapped in a soft blanket or feeling the gentle heat from your radiator. But tonight we will venture together into realms where the very concept of hot and cold breaks down in ways that challenge everything we thought we understood about the nature of reality. If this contemplative exploration helps you discover something fascinating about our universe, or simply provides a peaceful backdrop for reflection, your gentle support through likes, subscriptions, and thoughtful comments means more than you could imagine, creating a community of curious minds who find wonder in the impossible. Can you feel the temperature around you right now? That subtle sensation that tells your body whether to seek warmth or coolness? We will take our time tonight, allowing each concept to settle naturally in your mind without any pressure to grasp everything immediately, because the most profound discoveries in science often require patience and an openness to ideas that initially seem to defy logic. What we call temperature touches every moment of our lives, from the shiver that runs through us on a winter morning to the satisfying warmth of sunlight on our skin. Yet beneath these familiar sensations lies a deeper reality where particles dance in patterns too small to see and too fast to comprehend. Scientists have discovered that this dance has rules, boundaries that seemed absolute until brave. Researchers dared to look beyond them and found something extraordinary waiting in the shadows. Tonight we will explore how brilliant minds pushed past the supposed bottom of the temperature scale and discovered states of matter that should not exist, where the fundamental laws of thermodynamics reveal hidden chambers and secret passages that lead to realms more strange than fiction. The atoms surrounding you right now are performing an invisible ballet, moving with energies that correlate directly to what your skin perceives as warmth or cold. And understanding this connection opens doorways to mysteries that span from the smallest quantum effects to the largest cosmic phenomena. As we begin this exploration together, let yourself become aware of your own relationship with temperature, noticing how your body responds to thermal changes, how your comfort depends on the ceaseless motion of countless invisible particles that somehow create the sensation we call heat. The journey ahead will challenge our intuitions about what seems possible in nature, revealing how scientists learn to create conditions where conventional physics gives way to something far more mysterious and beautiful than anyone initially imagined possible. What transforms a perfectly ordinary winter morning into something that makes your entire body contract with involuntary shivers? And why does stepping outside on such days feel like entering an alien world where your breath becomes visible magic floating in crystalline air? Think about those moments when you reach for ice cubes from your freezer, feeling that sharp bite against your fingertips that sends signals racing up your arm. Or consider how your refrigerator maintains its cool interior by constantly humming with mechanical effort to push heat away from your food. These everyday encounters with cold represent just the surface layer of a phenomenon so fundamental that it shapes everything from the way water freezes into delicate, snowflake patterns to the reason why mountains wear caps of eternal snow while valleys below bloom with warm life. When goosebumps rise across your skin like tiny mountains of flesh, your body is responding to something far more profound than simple discomfort. engaging ancient survival mechanisms that recognize the subtle dance between your internal heat production and the endless appetite of the surrounding environment to steal that precious thermal energy away. Have you noticed how your breathing changes when exposed to truly frigid air? How each exhalation becomes a visible cloud of vapor that dissipates into the atmosphere like ghostly evidence of your body's internal fire? This visible breath reveals water molecules transitioning between states, condensing from invisible gas into tiny droplets that catch light and shimmer before vanishing, demonstrating the delicate balance between different phases of matter that cold conditions can trigger with remarkable precision. Your skin contains millions of temperature sensors, microscopic guardians that constantly monitor the thermal landscape around you, sending streams of information to your brain about whether you need to seek warmth, generate more internal heat through movement, or simply appreciate the refreshing sensation of coolness against overheated flesh. But there exists something much deeper happening when things get cold, something that reaches far beyond these familiar sensations into realms where the fundamental building blocks of reality begin to behave in increasingly strange and wonderful ways. The ice forming on your window during winter nights follows mathematical patterns that reflect the underlying crystalline structure of frozen water, creating fractal geometries that repeat at multiple scales, revealing how molecular forces organize matter into structures of breathtaking beauty and unexpected complexity. Every snowflake that falls represents a unique journey through atmospheric conditions, accumulating layers of ice according to temperature gradients and humidity levels that sculpt each crystal into patterns never before seen and never to be repeated exactly, making every winter storm a cosmic artist scattering billions of original masterpieces across the landscape. The mechanical humming of your refrigerator tells a story of thermodynamics in action, where electrical energy powers compressors that manipulate refrigerant chemicals to absorb heat from one location and dump it elsewhere, creating artificial winter conditions inside an insulated box, while generating waste heat that warms the surrounding kitchen air. These familiar cold experiences connect us to processes that extend throughout the natural world, from the formation of glaciers that carve valleys over geological time to the behavior of gases in the upper atmosphere where temperatures plummet to levels that would instantly freeze any liquid water into solid ice. Yet as remarkable as these everyday manifestations of cold might seem, they represent merely the beginning of a much stranger story about temperature, one that scientists have discovered by pushing their instruments and techniques toward the absolute limits of what seemed thermally possible. Moving gently from these recognizable sensations toward the science beneath, we find that temperature itself emerges from something even more fundamental than the motion of molecules, connecting to deep principles about energy, entropy, and the statistical behavior of matter that govern everything from stellar cores to laboratory experiments where researchers create conditions colder than anything naturally occurring in the known universe. Have you ever wondered what creates the warmth you feel when sunlight touches your skin? Or why a metal spoon becomes scorching hot when left in boiling soup? And could it be that these sensations arise from an invisible choreography performed by countless microscopic dancers moving at speeds that would astound you? Imagine attending a crowded party where everyone starts dancing energetically, bumping into each other with increasing frequency and vigor as the music tempo accelerates, creating a chaotic but somehow coordinated celebration of movement that fills the entire space with kinetic energy. Now picture what happens when that same party begins winding down, as people gradually slow their movements, reducing their collisions with neighbours, settling into gentler swaying motions that eventually fade into near stillness as the evening draws to its peaceful conclusion. This analogy captures something profound about the microscopic reality underlying every thermal experience you have ever encountered, because atoms and molecules behave remarkably like partygoers whose energy levels determine how vigorously they move through their molecular ballroom. When matter heats up, these atomic particles accelerate their motion like excited dancers responding to increasingly frantic music, spinning faster, vibrating more intensely, and colliding with their neighbours with greater force and frequency, creating the macroscopic effect we perceive as rising temperature. Conversely, cooling matter resembles a party where the music gradually slows, causing the molecular dancers to reduce their kinetic enthusiasm, moving with less violence and spending more time in relatively stable positions rather than careening wildly through their available space. You can think of temperature as measuring the average speed of this invisible dance, where billions upon billions of atomic performers contribute to a collective choreography that manifests as the thermal sensations your nervous system interprets as hot, warm, cool, or cold. The oxygen molecules floating in the air around you right now are racing through space at approximately 500 meters per second, faster than any supersonic aircraft, yet their individual journeys remain completely imperceptible to your senses, despite their extraordinary velocity and constant presence. These molecular speed demons collide with each other millions of times per second, exchanging energy through impacts that redistribute kinetic motion throughout the gas in patterns that statistical mechanics describes with elegant mathematical precision. Water molecules in your morning coffee execute a frenzied dance of rotation, vibration, and translation that correlates directly with the pleasant warmth you taste and feel, while the same molecules in an ice cube have slowed their choreography to gentler oscillations around fixed crystalline positions. The strange beauty lies in our complete inability to directly witness this perpetual atomic ballet, despite its fundamental role in creating every thermal experience that shapes our daily lives. From the comfort of heated homes to the refreshing coolness of swimming pools, consider how your body temperature remains remarkably stable even as the molecular dancers within your cells maintain their kinetic celebration at rates that would boggle your imagination, with proteins folding and unfolding, enzymes catalyzing biochemical reactions, and cellular machinery operating through thermal motion that never completely stops. Connecting these atomic phenomena to what we actually feel reveals one of nature's most elegant scaling relationships, where the statistical average of countless individual molecular velocities emerges as the macroscopic property we call temperature, bridging the gap between quantum mechanical reality and sensory experience. The metal handle of a pan becomes too hot to touch because rapidly vibrating atoms in the heated material transfer their kinetic energy to the molecules in your skin, creating a cascade of molecular acceleration that your pain receptors interpret as dangerous heat requiring immediate withdrawal. Even in the coldest environments humans have ever experienced, atomic motion continues relentlessly, though at reduced intensities that correspond to what we perceive as frigid conditions, demonstrating that the dance never truly stops, but simply changes its rhythm and amplitude. This microscopic perspective transforms our understanding of thermal phenomena from mysterious sensations into comprehensible consequences of particle physics, revealing how the behavior of individual atoms scales up to create the temperature-dependent world we navigate through touch, taste, and environmental awareness. The invisible choreography surrounding you at this very moment involves more dancers than there are stars in the observable universe, all participating in a cosmic ballet whose tempo determines whether you reach for a sweater or fan yourself to stay comfortable. Could there exist a temperature so profoundly cold that every atom in the universe would freeze into perfect stillness? And what would happen if brilliant scientists actually discovered the mathematical pathway leading to such an inconceivable destination? During the transformative decades of the 1840s and 1850s, a remarkable Scottish physicist named William Thomson, later elevated to Lord Kelvin, began investigating mysterious relationships between gas volumes and temperatures that would revolutionize humanity's understanding of thermal limits. Kelvin noticed that whenever researchers cooled various gases under controlled laboratory conditions, their volumes decreased in predictable mathematical patterns that suggested something extraordinary might await at the end of this progression. By carefully measuring how different gases contracted as temperatures dropped, plotting these observations on graphs, and extending the resulting lines backward through mathematical extrapolation, Kelvin realized that all gases seemed to converge toward a single universal point where their volumes would theoretically shrink to nothing. This convergence suggested the existence of an absolute thermal boundary, a fundamental flaw beneath which temperatures could not possibly descend, representing the ultimate limit of coldness that nature would permit anywhere in the cosmos. The calculations revealed this hypothetical boundary existed at precisely minus 273.15 degrees Celsius, equivalent to minus 459.67 degrees Fahrenheit, a temperature so extreme that no naturally occurring environment on Earth had ever approached such frigid conditions. Kelvin proposed establishing an entirely new temperature scale that would begin at this absolute minimum, designating it as 0 Kelvin, and creating a measurement system where negative values became impossible because nothing could exist beyond the fundamental thermal flaw he had discovered through mathematical reasoning. This absolute zero represents the theoretical place where atomic motion should simply cease, where the invisible molecular dance we explored earlier would slow to complete stillness, where particles would stop vibrating, rotating, and translating through space, creating a state of matter unlike anything observable in our everyday experience. Imagine cooling a gas until its constituent particles gradually reduce their kinetic enthusiasm, moving slower and slower like dancers responding to increasingly sluggish music, until finally they reach a point where motion itself becomes impossible due to the complete absence of thermal energy. The implications of Kelvin's discovery extended far beyond laboratory curiosity, suggesting that temperature possesses an absolute foundation analogous to how distance cannot be measured below 0 meters, or time cannot flow backward past a defined starting point, establishing fundamental limits that govern physical reality. Yet even as scientists celebrated this profound insight into nature's architecture, they began realizing that actually reaching absolute zero presented insurmountable challenges that revealed deeper mysteries about the quantum, mechanical foundations underlying thermal phenomena. The third law of thermodynamics, formulated decades later, would demonstrate that approaching absolute zero requires infinite amounts of work and infinite time, making this ultimate coldness eternally unreachable despite being mathematically well-defined and conceptually essential for understanding temperature itself. Every cooling process, no matter how sophisticated or powerful, can only asymptotically approach this limit, getting closer and closer while never quite achieving the perfect stillness that absolute zero represents, like trying to reach the horizon by walking toward it. Modern laboratories have achieved temperatures within billionths of a degree above absolute zero, creating conditions so cold that atoms behave according to bizarre quantum mechanical rules that completely contradict classical physics. Yet even these extraordinary achievements fall short of the theoretical perfection that Kelvin first envisioned. The impossibility of reaching absolute zero stems from fundamental quantum uncertainty principles that prevent particles from ever becoming completely motionless, ensuring that even at the coldest possible temperatures, tiny residual vibrations persist as ghostly reminders of the inherent restlessness built into the fabric of reality itself. This quantum motion, called zero-point energy, means that absolute stillness remains forever beyond our grasp, transforming Kelvin's mathematical destination into an eternally beckoning but unreachable goal that continues inspiring scientific exploration into the deepest mysteries of matter and energy. The bottom of everything thus becomes not a final stopping point, but rather a horizon that defines the ultimate limits within which all thermal phenomena must operate, establishing the foundation upon which our understanding of temperature, entropy, and the statistical behaviour of matter ultimately rests. Why did Lord Kelvin feel compelled to abandon the familiar Celsius and Fahrenheit scales that had served humanity for generations, and what profound insights emerge when we reimagine temperature measurement by starting from the absolute bottom rather than arbitrary reference points like freezing water? The revolutionary Kelvin scale represents a fundamental departure from conventional temperature thinking, establishing its 0 point at the theoretical limit where all molecular motion ceases, creating a measurement system that reflects the true thermal architecture of our universe rather than human convenience or historical accident. Unlike Celsius, which arbitrarily places 0 at water's freezing point, or Fahrenheit, which chose an obscure mixture of ice and salt as its baseline, the Kelvin scale anchors itself to physics itself, beginning measurements from the deepest possible cold and extending upward through all possible thermal states without ever allowing negative values. This approach transforms our perspective on familiar temperatures in ways that reveal hidden relationships between everyday thermal experiences and the fundamental laws governing matter and energy throughout the cosmos. Consider how room temperature, which feels perfectly moderate and comfortable to your human sensory system, actually registers around 300 Kelvin on this absolute scale, placing your cozy living space nearly 300 degrees above the foundation of thermal reality and revealing just how far removed ordinary life exists from the ultimate cold that defines temperature's lower boundary. This perspective shift suddenly makes apparent that what we consider normal, pleasant warmth represents an enormous thermal elevation above absolute zero, comparable to standing on a mountain nearly 300 meters high while considering the ground level far below. Your body temperature of approximately 310 Kelvin places you even further from the absolute foundation, demonstrating that biological processes require substantial thermal energy above the minimum possible level, to maintain the complex chemistry underlying consciousness, metabolism, and cellular function. When we examine the Sun using this absolute framework, its surface temperature of roughly 5,800 Kelvin becomes incomprehensibly far from stillness, representing thermal conditions so extreme that atoms exist in plasma states where electrons separate from nuclei, creating an environment where the familiar rules of chemistry completely break down. The nuclear fusion occurring within the Sun's core pushes temperatures to millions of Kelvin, creating conditions so energetic that hydrogen atoms overcome their mutual electrical repulsion and merge into helium, releasing the energy that ultimately powers nearly every biological and meteorological process occurring on Earth. This absolute temperature perspective reveals that the range between comfortable room temperature and the painful heat represents merely a tiny sliver of the vast thermal landscape extending from absolute zero to stellar extremes, fundamentally altering how we conceptualize hot and cold as relative rather than absolute sensations. The comfort of this scale lies in its ability to reveal universal patterns that remain hidden when using arbitrary reference points, demonstrating how all thermal phenomena follow consistent mathematical relationships when measured from the true foundation of temperature, rather than convenient but meaningless human conventions. Scientists have discovered that many fundamental physical constants and equations become elegantly simplified when expressed in Kelvin units, suggesting that nature itself operates according to principles that recognize absolute zero as the logical starting point for thermal measurements. The kinetic theory of gases, which describes how molecular motion relates to temperature, achieves mathematical beauty when temperatures are expressed as distances above absolute zero, revealing direct proportional relationships between thermal energy and average particle velocity that become obscured by offset scales. Thermodynamic calculations involving entropy, heat capacity, and phase transitions all benefit from the Kelvin scale's absolute foundation, allowing researchers to identify patterns and correlations that would remain invisible if temperatures were measured relative to arbitrary human reference points like water's freezing behavior under specific atmospheric conditions. Even the cosmic microwave background radiation that permeates all of space registers at approximately 2.7 Kelvin, demonstrating how astronomical observations naturally align with this absolute temperature framework and revealing the thermal signature of the universe's ancient history embedded in the fabric of space-time itself. This paradigm transformation shows that adopting nature's own reference frame for temperature measurements unveils hidden connections between disparate phenomena, from the quantum mechanical behavior of ultra-cold atoms to the thermonuclear processes powering distant stars, all operating within a single unified thermal landscape that extends from absolute stillness to energies beyond human imagination. What extraordinary phenomena emerge when brilliant scientists push matter to temperatures so close to absolute zero that atoms begin behaving according to rules that seem to violate common sense? And could these laboratory achievements at the very edge of thermal existence reveal secrets about reality that challenge our deepest assumptions about the nature of the universe? Modern laboratories have achieved temperatures measured in nanokelvin, which represents billionths of a degree above absolute zero, and even more remarkably, some experiments have reached picokelvin ranges, placing matter trillionths of a degree from the theoretical limit where all motion should cease. These achievements require sophisticated techniques that transform light itself into a cooling agent through processes so counterintuitive that they initially sound like science fiction rather than established laboratory practice. Laser cooling exploits the fact that atoms can absorb photons carrying specific energies, causing electrons to jump to higher energy levels before falling back down and emitting light in random directions, creating a net momentum transfer that gradually slows atomic motion through carefully orchestrated interactions between matter and electromagnetic radiation. Scientists arrange multiple laser beams from different directions, each tuned to frequencies slightly below the natural absorption lines of specific atoms, creating what researchers playfully call optical molasses, where particles become trapped in intersecting light fields that resist their motion like invisible quicksand. Magnetic trapping complements these optical techniques by using precisely shaped magnetic field gradients to confine ultra-cold atoms in invisible containers made entirely of electromagnetic forces, allowing researchers to isolate individual particles or small groups from environmental disturbances that would otherwise destroy the delicate quantum states emerging at these extreme temperatures. As atoms approach these incomprehensibly low thermal energies, They begin whispering rather than shouting their presence, moving so slowly that quantum mechanical effects normally masked by thermal noise become dramatically apparent, revealing the strange probabilistic nature underlying all matter at microscopic scales. Individual atoms start exhibiting wave-like properties that extend over distances large enough to overlap with neighbouring particles, creating collective quantum states where the identity of separate atoms becomes blurred into unified systems that behave according to principles completely foreign to classical physics expectations. Bose-Einstein condensation occurs when thousands of atoms surrender their individual identities and merge into a single quantum entity that occupies the lowest possible energy state available to the system, creating matter phases that exist nowhere naturally in the universe except in these carefully controlled laboratory environments. At these temperatures, ordinary concepts like particle position and velocity lose their classical meanings as uncertainty principles become macroscopically observable, demonstrating that the foundations of reality operate according to probabilistic rather than deterministic rules when examined at sufficient resolution and under appropriate conditions. Quantum entanglement between particles becomes readily achievable, creating correlations that Albert Einstein famously called spooky action at a distance, where measuring properties of one atom instantly influences the quantum state of its entangled partner, regardless of the spatial separation between them. These laboratory achievements have enabled unprecedented precision in horror. Atomic clocks, quantum computing research, and fundamental tests of quantum mechanics that probe the deepest mysteries about information, measurement, and the relationship between classical and quantum descriptions of physical phenomena. Yet even here, at the edge of nothing where matter barely maintains its grip on existence above the absolute thermal foundation, something impossible waits to challenge our understanding of temperature itself in the ways that early researchers never anticipated or imagined possible. The mystery deepens when scientists discover that certain systems can apparently achieve states that register as negative temperatures on the Kelvin scale, suggesting the existence of thermal realms beyond the supposed absolute limit that was thought to represent the ultimate boundary of coldness in our universe. These discoveries hint at hidden chambers in the thermal landscape where conventional rules break down and new physics emerges, revealing that our journey towards absolute zero merely represents the first stage of a more profound exploration into territories where temperature itself transcends the limitations that classical thermodynamics seem to establish as eternal and inviolable. But this remarkable story of pushing matter toward absolute stillness represents merely the beginning rather than the conclusion of humanity's quest to understand thermal extremes, because beyond the edge of classical temperature lies a realm where the impossible becomes not only possible, but experimentally reproducible, challenging everything we thought we knew about hot, cold, and the fundamental nature of thermal energy itself. What could possibly cause two respected physicists at Harvard University to question their own experimental apparatus, their measurement techniques, and perhaps even their sanity when their instruments began displaying temperature readings that violated fundamental laws supposedly governing thermal behavior throughout the entire universe? In the spring of 1951, Edward Purcell and Robert Pound were conducting seemingly routine nuclear magnetic resonance experiments in their laboratory at Harvard, working with lithium fluoride crystals subjected to carefully controlled magnetic field conditions as part of ongoing research into the quantum mechanical properties of atomic nuclei. These researchers had no intention of revolutionizing thermodynamics or challenging established scientific orthodoxy. They were simply investigating how nuclear spins respond to external magnetic influences, using techniques that had been successfully employed by countless previous investigators without generating any unusual or troubling results. The experimental setup involved placing crystalline lithium fluoride samples within powerful electromagnets capable of aligning the nuclear spins of lithium atoms, creating ordered magnetic states that could be manipulated and measured using radio frequency pulses and sophisticated detection, equipment available in post-war American universities. Purcell and Pound carefully prepared their crystals, calibrated their instruments, and began applying standard nuclear magnetic resonance protocols that should have yielded predictable, well-understood data consistent with established theoretical frameworks describing how nuclear magnetic moments interact with applied electromagnetic fields. However, as they monitored the thermal equilibrium of their nuclear spin systems using temperature measurement techniques specifically designed for such microscopic quantum systems, Something completely unexpected began appearing in their data that would force the scientific community to reconsider fundamental assumptions about the nature of temperature itself. The instruments were registering negative values on the Kelvin scale, readings that seemed to indicate their nuclear spin system had achieved temperatures below absolute zero, a physical impossibility according to every thermodynamics textbook written up to that point in scientific history. Initially, both researchers assumed their equipment must be malfunctioning because negative absolute temperatures represented a logical contradiction that violated basic principles taught to every physics student as immutable laws governing thermal behavior in all possible physical systems throughout the cosmos. They rechecked their magnetic field configurations, verified their radio frequency pulse sequences, and carefully examined every component of their experimental apparatus, searching for instrumental errors that could explain readings suggesting their lithium nuclei existed in thermal states colder than the supposed absolute limit of coldness itself. The temperature measurements remained stubbornly negative despite repeated calibrations and alternative measurement approaches, forcing Purcell and Pound to confront the possibility that their observations might reflect genuine physical phenomena rather than experimental artifacts or measurement mistakes. The nuclear spins in their lithium fluoride crystals appeared to be populating high-energy quantum states more frequently than low-energy alternatives, creating an inverted distribution that resembled thermal equilibrium at negative absolute temperatures according to statistical mechanical calculations governing the relationship between energy and probability in quantum system. This population inversion suggested that their nuclear spin system had somehow transcended the thermal boundaries established by classical thermodynamics, existing in states where conventional concepts of hot and cold ceased to apply in expected ways. The researchers faced a profound dilemma. Either their experimental observations were fundamentally flawed due to unknown systematic errors, or the scientific understanding of temperature itself contained gaps that allowed for thermal states beyond the supposed absolute lower limit that defined the foundations of all previous thermodynamic theory. Their initial reaction combined skepticism with growing excitement as they realized that genuine negative absolute temperatures would represent a discovery of profound significance for both fundamental physics and practical applications involving thermal energy manipulation and quantum state engineering. The implications extended far beyond nuclear magnetic resonance experiments, suggesting that other physical systems might also achieve thermal states that transcended classical limitations, opening entirely new territories for scientific exploration and technological development. Purcell and Pound found themselves at the center of a scientific revolution that would challenge textbook presentations of thermodynamics and force physicists to develop more sophisticated theoretical frameworks capable of accommodating thermal phenomena that seemed impossible according to conventional wisdom accumulated over centuries of careful experimental investigation. Have you ever held a compass and watched its needle swing toward magnetic north, responding to invisible forces that seem to reach across vast distances? And could it be that every atomic nucleus contains its own miniature version of this magnetic pointer, capable of orienting itself in ways that create entirely new possibilities for thermal behavior? Picture each atomic nucleus as containing a microscopic compass needle, an internal magnetic moment that can point in different directions depending on the electromagnetic environment surrounding it, behaving like an impossibly tiny bar magnet embedded at the heart of every atom throughout your body and everything around you. These nuclear magnetic moments arise from quantum mechanical properties of protons and neutrons that combine to create net angular momentum, generating magnetic dipoles thousands of times smaller than the smallest compass you could imagine, yet following similar principles of orientation and response to external magnetic influences. When scientists apply powerful external magnetic fields to materials like lithium fluoride crystals, these microscopic nuclear compasses begin aligning themselves with the imposed electromagnetic environment, just as your household compass needle swings to point northward when influenced by Earth's magnetic field. Except that quantum mechanics governs the possible orientations rather than classical physics. Unlike macroscopic compass needles that can point in any direction within a continuous range of angles, nuclear spins are restricted to discrete quantum states, typically limited to either pointing parallel or anti-parallel to the applied magnetic field, creating a binary system where each nucleus must choose between two specific energy configurations. The parallel orientation, where the nuclear magnetic moment aligns with the external field, represents the lower energy state, analogous to a compass needle resting comfortably in its natural northward position, while the Antiparallel orientation requires additional energy to maintain, like forcing a compass needle to point southward against its natural tendency. This energy difference between parallel and antiparallel nuclear spin states becomes the crucial factor that enables negative absolute temperatures to emerge under appropriate experimental conditions, because quantum statistics govern how many nuclei occupy each available energy level at thermal equilibrium. The remarkable isolation of nuclear spins from other atomic motion creates a unique situation where these microscopic magnetic systems can achieve thermal states completely independent from the translational and vibrational energy of the atoms themselves, allowing nuclear magnetic moments to reach equilibrium temperatures different from their surrounding molecular environment. This separation occurs because nuclear magnetic interactions operate on much slower timescales than electronic or vibrational processes, meaning that nuclear spins can maintain their own distinct thermal distribution while the rest of the atom continues following conventional thermal behavior according to classical statistical mechanics. Imagine a ballroom where different groups of dancers follow completely separate musical rhythms, with one ensemble responding to slow, stately classical music while another group moves to rapid modern beats, creating two independent thermal systems sharing the same physical space yet maintaining distinct energy distributions. The nuclear spins represent the slow dancers whose magnetic orientations change gradually in response to applied electromagnetic fields, while the electronic and vibrational motions correspond to the rapid dancers whose kinetic energy reflects normal thermal conditions throughout the crystal lattice structure. This temporal decoupling allows researchers to manipulate nuclear spin populations using magnetic field techniques without directly affecting other forms of atomic motion, creating conditions where the nuclear magnetic system can achieve population inversions that would be impossible if all atomic degrees of freedom remained strongly coupled. When external magnetic fields suddenly reverse direction or change intensity, the nuclear spins require finite time to adjust their orientations, during which period they can exist in non-equilibrium distributions that correspond to negative absolute temperatures on the nuclear magnetic energy scale. The paradox emerges because these nuclear spin systems possess upper limits to their possible energies, unlike conventional thermal systems where particles can achieve arbitrarily high kinetic energies through sufficient heating, creating bounded energy spectra that enable population inversions where more nuclei occupy high-energy antiparallel orientations than low-energy parallel states. This fundamental difference between bounded and unbounded energy systems becomes the key to understanding how negative absolute temperatures can exist for nuclear spins while remaining impossible for ordinary thermal motion, setting up the conceptual framework necessary for comprehending how Purcell and Pound's experimental observations violated conventional thermodynamic expectations while remaining physically valid within appropriate theoretical contexts. What strange twist of physics could possibly convince more people to climb to the exhausting summit of a mountain rather than settle comfortably in a peaceful valley below? And how might this seemingly impossible social scenario mirror the bizarre quantum mechanical behavior that enables negative absolute temperatures to exist in laboratory experiments? Under normal thermal circumstances throughout nature, particles consistently choose lower energy states over higher alternatives, following statistical preferences analogous to humans naturally gravitating toward comfortable valley locations, rather than struggling toward challenging mountaintop destinations that require significant effort to reach and maintain. This universal tendency reflects the Boltzmann distribution, a mathematical relationship discovered by Austrian physicist Ludwig Boltzmann that describes how thermal energy spreads among available quantum states according to exponential probability functions that strongly favor configurations requiring minimal energy investment. The Boltzmann factor, expressed mathematically as an exponential function containing the ratio between state energy and thermal energy, ensures that low-energy configurations become exponentially more probable than high-energy alternatives as temperature decreases, creating the familiar thermal landscape where most particles occupy ground states while progressively fewer populate excited levels. Imagine a mountainous terrain where gravity naturally pulls most hikers into valleys and meadows, leaving only adventurous individuals willing to expend extra effort climbing toward peaks, with the proportion of summit seekers decreasing exponentially as elevation increases and the physical demands become more challenging to overcome. This gravitational analogy captures the essence of normal thermal distributions, where energy differences between quantum states create barriers that most particles cannot overcome at typical temperatures, resulting in population patterns that concentrate matter in low-energy configurations while leaving high-energy states relatively empty according to statistical mechanical principles. However, population inversion represents a complete reversal of these natural tendencies, creating conditions where more particles occupy high-energy states than their low-energy counterparts, analogous to discovering a mysterious force that drives most hikers to abandon comfortable valleys and struggle toward mountain summits despite the increased difficulty and energy expenditure required. This phenomenon violates our intuitive expectations about thermal equilibrium because it suggests that particles actively seek energetically expensive configurations rather than settling into the most accessible and stable alternatives available within their quantum mechanical environment. The mathematical signature of population inversion appears when the normal Boltzmann distribution becomes inverted, with exponential probability factors favoring high-energy states over low-energy alternatives, creating a statistical pattern that corresponds to negative absolute temperatures according to thermodynamic definitions relating thermal energy to entropy gradients. When scientists observe more nuclear spins, pointing anti-parallel to applied magnetic fields than parallel orientations, despite the anti-parallel configuration requiring additional energy to maintain against natural magnetic tendencies, they witness direct evidence of population inversion that challenges fundamental assumptions about thermal behavior in quantum systems. This energetic preference reversal occurs because nucleus spin systems possess finite numbers of available quantum states, unlike classical thermal systems where particles can achieve arbitrarily high kinetic energies through unlimited acceleration processes that create unbounded energy spectra extending toward infinity. The bounded nature of nuclear magnetic energy levels means that once all spins reach maximum possible energies by adopting anti-parallel orientations, further energy input cannot increase individual particle energies but instead must redistribute among available states in ways that can decrease total system entropy. This entropy reduction accompanies energy increases, represents the thermodynamic signature of negative absolute temperature, where adding thermal energy to the system actually reduces its disorder, rather than increasing randomness as occurs in conventional thermal processes governed by classical statistical mechanics. The flip from normal to inverted population distributions marks a phase transition between positive and negative temperature regimes, crossing through infinite temperature where all available energy states become equally populated before continuing into negative territory, where high energy states dominate statistical distributions. Understanding why this matters requires recognizing that temperature fundamentally measures the relationship between energy and entropy, rather than simply reflecting average particle velocities, meaning that population inversion creates thermal conditions where conventional intuitions about hot and cold cease to apply in expected ways. Systems exhibiting negative absolute temperatures become hotter than any positive temperature system, transferring energy to conventional matter despite existing at nominally lower Kelvin values, demonstrating that temperature scales possess hidden complexities that extend beyond simple numerical ordering from cold to hot. These discoveries revealed that thermodynamic principles contain subtleties overlooked by classical physics, opening new territories for scientific exploration, where quantum mechanics enables thermal phenomena impossible within purely classical theoretical frameworks, fundamentally expanding our understanding of energy, entropy, and temperature relationships in exotic matter phases. What if everything you believed about temperature from childhood thermometer readings and weather reports represents merely the surface layer of a far more profound and counterintuitive reality that governs the fundamental relationship between order, chaos, and energy throughout the entire universe? Most people develop their understanding of thermal phenomena by associating temperature with the average speed of microscopic particles, imagining atoms and molecules racing around faster when things feel hot and slowing down when conditions become cold, creating a seemingly straightforward connection between kinetic motion and thermal sensation. This particle velocity interpretation works reasonably well for explaining everyday experiences like why metal feels cold to touch or why soup cools after sitting on the counter. But it fails to capture the deeper thermodynamic principles that actually define temperature according to the mathematical foundations underlying all thermal physics. The profound truth emerges when we recognize that temperature fundamentally measures how systems balance energy against entropy, rather than simply reflecting average particle velocities, revealing a relationship so subtle that it remained hidden from scientific understanding until statistical mechanics evolved sophisticated mathematical frameworks capable of describing thermal behavior at microscopic scales. Entropy represents the degree of disorder within any system, quantified by counting the total number of different ways that constituent particles can arrange themselves while maintaining the same overall energy content, creating a measure of randomness that increases as systems evolve toward more probable configurations. Imagine having a deck of cards where entropy corresponds to the number of possible arrangements, with a perfectly ordered sequence representing minimum entropy, while completely shuffled configurations maximize disorder through countless alternative arrangements that appear equally random to outside observers. When energy flows into a typical system, it usually increases both the average particle speeds and the total number of accessible quantum states, causing entropy to rise alongside temperature in the familiar pattern that governs normal thermal processes throughout everyday experience and most scientific applications. However, the mathematical definition of temperature emerges from calculating how entropy changes relative to energy variations, expressed as the derivative of energy with respect to entropy while holding other system properties constant, creating a precise relationship that transcends simple particle velocity considerations. This fundamental connection appears mathematically as temperature equals the change in energy divided by the corresponding change in entropy, establishing a thermodynamic definition that remains valid even when conventional particle speed interpretations break down in exotic quantum systems or unusual physical configurations. The significance of this deeper understanding becomes apparent when considering systems where energy increases can actually decrease entropy rather than increasing disorder, creating conditions where the mathematical temperature definition yields negative values despite particles continuing to move according to quantum mechanical principles. Such entropy-reducing energy additions occur in systems with bounded energy spectra, where particles cannot achieve arbitrarily high velocities but instead must redistribute among finite numbers of available quantum states, leading to population inversions that represent more ordered configurations at higher total energies. Consider a system where adding energy forces particles into increasingly structured arrangements rather than promoting random motion, analogous to adding heat that somehow causes a shuffled deck of cards to spontaneously organize itself into numerical sequences rather than becoming more thoroughly mixed. These special circumstances reveal that temperature reflects the fundamental trade-off between energy and order within any physical system, operating according to mathematical principles that extend far beyond simple associations with particle velocities or thermal cetaceans accessible through human sensory experience. The entropy-energy relationship opens conceptual doors to negative temperature regimes because mathematical derivatives can yield negative results when energy increases, correspond to entropy decreases, creating thermodynamic states where conventional thermal intuitions cease to apply while remaining perfectly consistent with rigorous statistical mechanical theory. Understanding temperature as an entropy gradient rather than a velocity measure explains why negative absolute temperatures become physically possible under appropriate conditions, why such states transfer energy to positive temperature systems despite appearing numerically colder, and why population inversions represent genuine thermal equilibrium rather than temporary disturbances requiring external intervention. This paradigm shift transforms temperature from a familiar but superficial concept into a window through which we glimpse the deep mathematical structures governing how energy, information, and probability interact within quantum mechanical systems that operate according to principles extending far beyond everyday thermal experience, revealing hidden connections between thermodynamics, statistical mechanics, and the fundamental laws shaping physical reality at microscopic scales, where classical intuitions must surrender to more sophisticated mathematical descriptions of natural phenomena. Why do some physical systems behave like infinite staircases where particles can climb to arbitrarily high energy levels, while others resemble closed rooms with rigid ceilings that impose absolute limits on how much energy individual components can possibly possess? In most familiar material systems throughout our everyday experience, particles enjoy unlimited potential for kinetic acceleration, capable of moving faster and faster without encountering fundamental barriers that prevent additional energy absorption, creating what physicists call unbounded energy spectra that extend infinitely upward from their ground states. Consider gas molecules in ordinary air, which can theoretically achieve any velocity up to the speed of light through sufficient heating processes, meaning that thermal energy additions always result in increased average particle speeds and expanded ranges of accessible motion within the available space. These unbounded systems follow conventional thermodynamic behavior, because adding energy consistently increases both particle velocities and the total number of ways molecules can distribute themselves among available momentum states, causing entropy to rise alongside temperature in predictable mathematical relationships. Electrons orbiting atomic nuclei similarly possess unlimited possibilities for excitation into higher energy levels, with each successive orbital requiring more energy, but never encountering absolute upper bounds that would prevent further promotion through continued energy input from external sources. However, certain special physical configurations impose strict maximum energy limits that create bounded quantum spectra, where particles cannot absorb additional energy beyond specific thresholds, regardless of how much thermal energy researchers attempt to supply through heating or electromagnetic stimulation. The nuclear spin systems discovered by Purcell and Pound exemplify these bounded energy situations perfectly, because nuclear magnetic moments can only orient themselves parallel or anti-parallel to applied magnetic fields, creating binary quantum states with no intermediate possibilities or higher energy alternatives available for occupation. Picture these nuclear spin nears as switches that can only exist in on or off positions, rather than adjustable dimmers capable of infinite intermediate settings, constraining each nucleus to choose between exactly two energy configurations separated by fixed gaps, determined by magnetic field strength and fundamental nuclear properties. This binary limitation means that once all nuclear spins reach their maximum energy antiparallel orientations, no additional energy can be stored within the nuclear magnetic system, creating an absolute ceiling that prevents further thermal energy absorption despite continued external heating efforts. The fascinating physics emerges when systems approach these energy ceilings, because adding thermal energy beyond the point where most particles occupy maximum available states begins producing counterintuitive effects that violate conventional thermodynamic expectations about the relationship between energy input and entropy changes. As more nuclear spins flip from low-energy parallel orientations to high-energy anti-parallel configurations, the system initially behaves normally, with entropy increasing alongside energy, according to familiar statistical mechanical principles governing thermal equilibrium distributions. However, something remarkable occurs when energy additions push the majority of spins into anti-parallel orientations, because further energy input starts creating more ordered rather than more disordered configurations by forcing additional spins into the same high-energy state. This transition represents the crucial inversion point where adding energy actually decreases entropy instead of increasing disorder, violating the normal correlation between thermal energy and randomness that governs unbounded systems throughout conventional thermal physics. Imagine filling a theatre where early arrivals scatter randomly throughout available seating, creating maximum disorder and entropy, but late arrivals must squeeze into remaining seats near the stage, producing more organised seating patterns despite higher total occupancy representing increased energy investment. The mathematical consequence of this entropy reduction accompanying energy increases appears as negative temperature, according to thermodynamic definitions relating thermal gradients to energy entropy derivatives, creating thermal states that exist beyond infinite temperature on the extended Kelvin scale. When all nuclear spins achieve anti-parallel orientations representing maximum possible energy within the bounded quantum spectrum, the system reaches a state analogous to perfect crystalline order, where entropy approaches zero despite extremely high energy content, demonstrating how bounded spectra enable thermal behavior impossible within unlimited energy systems. These bounded energy scenarios reveal that negative absolute temperatures represent genuine equilibrium states rather than temporary disturbances, because systems naturally evolve toward maximum entropy configurations within their available energy ranges, which can correspond to population inversions when energy spectra possess upper limits. The key insight involves recognizing that energy bounds fundamentally alter the relationship between thermal energy and disorder, creating circumstances where conventional thermodynamic intuitions must yield to more sophisticated understanding of how quantum mechanical constraints influence statistical mechanical behavior in exotic matter phases that push physical systems beyond familiar thermal territories. Could the familiar temperature scale that governs everything from weather forecasts to cooking instructions actually represent only half of a complete thermal's landscape, with an entire hidden realm extending beyond infinite heat into territories where conventional hot and cold concepts transform into something far stranger yet mathematically elegant. Rather than ending at infinite temperature as classical physics suggested, the complete thermal scale follows a continuous pathway that begins at absolute zero, ascends through all positive Kelvin values toward positive infinity, then seamlessly transitions through negative infinity before descending through increasingly warm negative temperatures back toward absolute zero approached from above. This extended temperature framework reveals that what we consider the hottest possible conditions at positive infinity actually connect directly to the coldest possible negative temperatures at negative infinity, creating a thermal topology more resembling a circle than the linear progression most people imagine when thinking about hot and cold extremes. The counterintuitive reality emerges when we recognize that negative absolute temperatures represent states hotter than any positive temperature value, no matter how large, because systems at negative temperatures spontaneously transfer energy to any positive temperature environment they encounter, behaving as inexhaustible heat sources that violate conventional thermal intuitions. Imagine discovering that what appeared to be the ultimate summit of a mountain actually opens onto a hidden plateau extending infinitely in the opposite direction, where every location on this reverse landscape sits higher than the tallest peaks visible from normal climbing approaches. Heat always flows from negative temperature systems toward positive temperature environments, following thermodynamic principles that remain consistent even when temperature values appear numerically confusing according to conventional ordering expectations based on familiar number line relationships. A system at negative 100 Kelvin spontaneously heats any object at positive 1 million Kelvin, demonstrating that thermal flow depends on the fundamental thermodynamic definition of temperature rather than simple numerical comparisons that might suggest cold should flow toward hot according to magnitude relationships. This seemingly paradoxical behavior resolves when we understand that negative temperatures exist beyond positive infinity on the extended scale, occupying thermal territories that conventional physics never explored, because bounded energy systems required for negative temperatures rarely occur naturally throughout most observable physical phenomena. The circular nature of this extended temperature scale emerges from mathematical topology underlying statistical mechanics, where temperature represents not a simple linear quantity, but rather a position on a continuous loop connecting absolute zero through positive infinity to negative infinity, and back to absolute zero from the opposite direction. Consider how compass directions form a circle where continuing past north eventually leads back to north from the south, except that temperature circles connect thermal extremes through infinity rather than simple geographical orientations accessible through ordinary spatial navigation. This circular thermal topology provides conceptual comfort by revealing that negative absolute temperatures follow logical mathematical rules rather than representing arbitrary exceptions to thermodynamic principles, demonstrating that extended temperature scales emerge naturally from rigorous statistical mechanical theory applied to bounded energy systems. The strange extension preserves fundamental thermodynamic relationships while expanding the thermal landscape to accommodate physical phenomena that classical theory could not properly describe, creating a more complete theoretical framework capable of explaining exotic quantum states achieved in modern laboratory experiments. Temperature differences continue determining heat flow, directions according to established thermodynamic principles, with energy always moving from higher to lower temperature regions when those terms are properly understood within the context of extended thermal scales that include negative regimes. Entropy considerations provide additional insight into why negative temperatures exceed positive values in terms of thermal intensity, because systems achieving population inversions through energy saturation of bounded quantum spectra represent more energetically excited configurations than any unbounded system could achieve through conventional heating processes. The mathematical elegance of circular temperature scales reveals deep connections between thermal physics and abstract mathematical concepts like topology and continuous transformations, suggesting that natural phenomena often follow patterns more sophisticated than initial observations might indicate to researchers working within limited theoretical frameworks. Understanding temperature as circular rather than linear transforms our conceptual relationship with thermal phenomena, revealing hidden symmetries and unexpected connections that bridge classical thermodynamics with quantum mechanical effects emerging in exotic matter phases produced under extreme laboratory conditions. This extended thermal landscape demonstrates how scientific understanding evolves by discovering that familiar concepts like temperature contain hidden depths and unexpected extensions that emerge when theoretical frameworks develop sufficient mathematical sophistication to describe physical phenomena operating beyond everyday experience, opening conceptual doors to thermal regimes where conventional wisdom must surrender to more nuanced appreciation of natural complexity. What revolutionary breakthrough could possibly convince a team of German physicists to attempt something that decades of theoretical work suggested might be fundamentally impossible? And how did their audacious 2013 experiment transform negative absolute temperature from an exotic curiosity limited to nuclear magnetic systems into a phenomenon affecting the actual motion of atoms through space? At the Ludwig Maximilians University in Munich and the Max Planck Institute for Quantum Optics, an extraordinary research collaboration led by Ulrich Schneider and Emanuel Bloch began pursuing an ambitious goal that would extend negative temperature physics far beyond the nuclear spin systems where such phenomena had remained confined since Purcell and Pound's groundbreaking discoveries 6 decades earlier. Their team recognized that achieving negative temperatures in the translational motion of atoms themselves would represent a monumental advance because kinetic energy systems had always been considered unbounded, lacking the finite energy spectra essential for population inversion effects that enable thermal states beyond positive infinity on the extended temperature scale. The experimental challenge required creating artificial boundaries for atomic motion, essentially building invisible walls that would constrain kinetic energy within finite ranges analogous to how nuclear spins remain limited to binary orientational choices within applied magnetic field environments. Schneider, Bloch, and their colleagues began with ultra-cold atoms cooled to temperatures measured in billionths of a Kelvin, starting from thermal conditions already approaching the quantum mechanical regime, where individual particle behavior becomes governed by wave-like properties rather than classical trajectory dynamics. These potassium atoms had been laser-cooled and magnetically trapped, using techniques representing decades of advances in atomic physics, creating pristine quantum systems where environmental disturbances could be minimized, and precise control over atomic states becomes experimentally achievable through sophisticated electromagnetic manipulation protocols. The breakthrough innovationists involved optical lattice seekers created by interfering laser beams to produce standing wave patterns of electromagnetic intensity that act like three-dimensional egg cartons for atoms, providing periodic potential energy landscapes where particles become confined to specific spatial regions while retaining limited mobility between adjacent sites. These optical lattice structures function as artificial crystals made entirely of light, where laser intensity variations create energy barriers and valleys that constrain atomic motion within controllable ranges, effectively imposing upper limits on kinetic energy that transform unbounded translational systems into bounded quantum spectra suitable for negative temperature physics. The laser wavelengths, intensities, and polarization states were carefully tuned to create optical potentials deep enough to prevent atoms from escaping while shallow enough to permit controlled quantum tunneling between neighboring lattice sites, balancing confinement against mobility in ways that preserve the essential physics underlying negative temperature phenomena. By adjusting the strength of interactions between trapped atoms using magnetic field variations near Feshbach resonances, the research team could switch atomic interactions from repulsive to attractive, creating conditions where particles naturally tend to cluster rather than spread apart according to normal thermal distribution patterns. The experimental sequence involved rapidly changing these interaction parameters while atoms occupied high energy bands within the optical lattice structure, forcing the system through non-equilibrium dynamics that culminated in stable negative temperature states, where more atoms possessed high kinetic energies than low kinetic alternatives. Their remarkable achievement demonstrated that negative absolute temperatures could indeed be realized for the actual translational motion of atoms, rather than remaining limited to internal nuclear or electronic degrees of freedom, proving that kinetic energy systems could be artificially bounded through appropriate experimental design using optical lattice confinement techniques. The momentum distribution measurements revealed clear signatures of population inversion, with atomic clouds exhibiting preferential occupation of high momentum states at the edges of allowed energy bands, rather than concentrating around zero momentum as conventional thermal distributions would predict. This breakthrough extended negative temperature physics into entirely new territory by showing that fundamental motional degrees of freedom could achieve thermal states beyond positive infinity, opening possibilities for exploring exotic quantum many-body physics in regimes previously considered theoretically interesting but experimentally inaccessible. The Munich team had successfully created the first negative temperature system involving actual particle motion through space, transcending the limitations of nuclear spin systems and demonstrating that negative absolute temperatures represent a general thermodynamic phenomenon applicable to any physical system with appropriately bounded energy spectra, regardless of whether those bounds arise naturally or through clever experimental engineering. How do scientists transform ordinary potassium atoms from everyday matter into exotic quantum ingredients capable of achieving thermal states that violate everything we learned about hot and cold, and what precise combination of techniques allows researchers to orchestrate this remarkable transformation with sufficient control to verify their impossible results? The experimental recipe begins with ingredient 1, ultra-cold potassium atoms confined within sophisticated magnetic trap architectures that isolate these quantum particles from environmental disturbances while maintaining temperatures mere billionths of degrees above absolute zero through carefully orchestrated laser cooling protocols. These magnetic confinement systems employ precisely shaped electromagnetic field gradients that create invisible containers capable of holding clouds of neutral atoms without physical walls, using the magnetic dipole moments of individual potassium atoms to provide restoring forces that counteract thermal motion and gravitational effects. The trapped atomic ensemble must be prepared with exquisite purity, containing thousands of identical potassium-39 isotopes, whose quantum mechanical properties have been characterized through decades of atomic physics research, ensuring that experimental parameters can be controlled with precision necessary for reproducible negative temperature generation. Ingredient 2 involves creating optical lattices through interference patterns produced by multiple laser beams intersecting at carefully calculated angles, generating standing wave configurations that produce periodic intensity variations resembling three-dimensional honeycomb structures made entirely of electromagnetic radiation. These optical lattice potentials emerge from the interaction between atomic polarizability and spatially varying electric field amplitudes, creating energy landscapes where atoms experience forces analogous to rolling marbles moving through egg carton depressions separated by controllable barrier heights. The laser wavelengths must be detuned from atomic resonance frequencies to avoid unwanted excitation effects, while maintaining sufficient intensity to create potential depths capable of confining atomic motion within individual lattice sites, balancing optical forces against quantum tunneling effects that allow controlled intersite transport. Ingredient 3 employs Feshbach resonance techniques that exploit magnetic field dependencies of atomic scattering, properties to tune interaction strengths between trapped particles from strongly repulsive to strongly attractive regimes through precise electromagnetic control over collision dynamics. These resonance phenomena occur when bound molecular states approach threshold energies for atomic pair formation, allowing experimenters to continuously adjust the effective interaction potential by varying applied magnetic field intensities according to well-characterized resonance maps determined through previous spectroscopic investigations. The experimental process involves initially loading ultra-cold atoms into optical lattice sites under conditions where interparticle interactions remain weakly repulsive, allowing the quantum gas to equilibrate into conventional thermal distributions, where low-energy motional states become preferentially occupied according to normal Boltzmann statistics. The crucial manipulation occurs when researchers rapidly flip interaction parameters from repulsive to attractive regimes, while simultaneously exciting atoms into higher energy bands within the optical lattice spectrum, creating non-equilibrium conditions that drive the system toward negative temperature equilibrium configurations. This parameter switching must occur faster than natural equilibration timescales, but slower than individual atomic response times, requiring precise temporal control over magnetic field variations and optical lattice depths to guide the quantum many-body system through the desired thermodynamic transformation. Momentum distribution measurements provide the primary experimental signature for verifying negative temperature achievement, revealing population inversions where high momentum states contain more atoms than low momentum alternatives, contrary to conventional thermal expectation patterns. These measurements employ time-of-flight imaging techniques, where researchers suddenly release atoms from optical confinement and photograph their spatial distribution after ballistic expansion, with initial momentum values directly corresponding to final position coordinates through well-understood classical mechanics relationships. The verification process requires multiple independent confirmation methods, including energy measurements, correlation function analysis, and comparison with theoretical predictions from quantum many-body simulations that model the complete experimental sequence using established computational techniques. Researchers performed extensive systematic studies varying experimental parameters like lattice depth, interaction strength, and preparation protocols to demonstrate reproducibility and rule out alternative explanations for their observations, accumulating statistical evidence sufficient to convince the broader scientific community. Additional verification came through temperature measurements using thermometry techniques specifically designed for quantum many-body systems, confirming that momentum distribution inversions corresponded to genuine negative absolute temperatures rather than non-thermal artifacts that might mimic population inversion signatures without representing true thermodynamic equilibrium states. The impossible achievement required years of experimental optimization, theoretical modeling, and careful systematic investigation to establish beyond reasonable doubt that kinetic motion itself could indeed achieve thermal states extending beyond positive infinity into the mysterious realm of negative absolute temperatures. What visual evidence could possibly convince skeptical physicists that atoms have achieved the impossible feat of existing at temperatures below absolute zero? And how do these exotic quantum states manifest themselves through observable signatures that distinguish negative temperature systems from any conventional thermal phenomenon ever documented in scientific literature? The most striking experimental signature appears in momentum distribution measurements that reveal completely inverted population patterns, where fast-moving particles vastly outnumber their slow-moving counterparts, creating spectral profiles that look like conventional. Thermal distributions turn completely upside down through some mysterious quantum mechanical transformation. Instead of observing the familiar bell-shaped curves centered around zero momentum that characterizes normal thermal equilibrium, researchers witness bizarre double-peaked structures where atomic populations concentrate at the highest allowed momentum. Values while leaving the central low-energy region conspicuously depleted of particles. These inverted distributions violate every intuitive expectation about how thermal energy should spread among available quantum states, because conventional wisdom suggests that most particles should occupy comfortable low-energy configurations rather than struggling to maintain energetically expensive high-momentum conditions. The momentum peaks appear precisely at the boundaries of energy bands created by optical lattice confinement, demonstrating that atoms preferentially occupy the most energetic states accessible within their artificially bounded kinetic energy spectrum rather than settling into ground state configurations. Stable attraction presents another paradoxical feature where particles experience mutual gravitational-like forces that should theoretically cause catastrophic collapse. Yet the negative temperature system maintains structural integrity through quantum mechanical effects that prevent gravitational instability despite attractive interparticle interactions. This stability emerges because quantum uncertainty principles create effective pressure that counteracts attractive forces, establishing equilibrium conditions where clustering tendencies balance against quantum mechanical resistance to spatial localization in ways that classical physics cannot adequately describe. The atomic cloud wants to contract under attractive interactions but cannot overcome quantum pressure effects that arise from momentum distribution inversions, creating a delicate balance between competing forces that maintain system stability over experimentally relevant timescales. Negative pressure represents perhaps the most counterintuitive aspect of these exotic states, where the system simultaneously pushes outward against external constraints, while experiencing internal attractive forces that pull constituent particles toward collective clustering, creating thermodynamic conditions analogous to dark energy effects hypothesized to drive cosmic acceleration. This pressure inversion occurs because negative temperature systems respond oppositely to volume changes, compared with conventional matter, expanding when compressed and contracting when allowed additional space, violating mechanical intuitions developed through lifelong experience with positive temperature materials. The equation of state-governing negative temperature matter exhibits properties that seem to defy common sense, because increasing system density actually reduces internal pressure, while expansion increases the force exerted against external boundaries creating thermodynamic behavior unlike anything encountered in ordinary engineering applications. Temporal stability of negative temperature states surprised researchers who initially expected such exotic configurations to rapidly decay into conventional thermal distributions through natural relaxation processes driven by environmental coupling and quantum decoherence effects. However, carefully isolated systems can maintain population inversions for hundreds of milliseconds, representing thousands of natural oscillation periods during which negative temperatures persist as genuine equilibrium states rather than transient non-equilibrium artifacts that quickly dissipate through irreversible thermalization. This remarkable longevity demonstrates that negative temperature represents a stable thermodynamic phase rather than an unstable excited state, proving that these exotic thermal conditions can exist as robust physical phenomena worthy of detailed experimentals, investigation and theoretical analysis. The characteristic signature peaks appearing at momentum distribution edges provide unambiguous experimental evidence for negative temperature achievement because such edge-enhanced population patterns cannot arise through any known mechanism other than thermal equilibrium at negative absolute temperatures. These peaks exhibit the precise mathematical form predicted by statistical mechanical theory applied to bounded energy systems, with exponential population factors that correspond exactly to Boltzmann distributions evaluated using negative temperature parameters rather than conventional positive values. The sharpness and symmetry of these edge peaks reflect the high degree of thermal equilibrium achieved within the negative temperature regime, demonstrating that the system has reached genuine thermodynamic stability rather than maintaining artificial population distributions through continuous external driving or non-equilibrium pumping mechanisms. Multiple independent experimental confirmations using different measurement techniques all yield consistent results that support the interpretation of these observations as representing authentic negative absolute temperatures and kinetic motion rather than alternative explanations involving measurement artifacts, systematic errors, or misidentified quantum phenomena that might superficially resemble population inversion signatures. What fundamental assumptions about energy conversion and mechanical work would need to be completely abandoned if engineers could design heat engines that extract more useful work than the thermal energy supplied by their primary fuel source? And could such seemingly impossible devices actually comply with conservation laws while violating every engineering principle taught in thermodynamics textbooks? Traditional heat engines operating between conventional thermal reservoirs face absolute efficiency limitations described by Carnot's theorem, which establishes that no cyclic process can convert thermal energy into mechanical work with efficiency exceeding the theoretical maximum determined solely by the temperature difference between hot and cold reservoirs according to the fundamental thermodynamic principles. The famous Carnot efficiency formula reveals that even perfectly reversible engines operating without friction, heat loss or other practical inefficiencies cannot achieve 100% conversion of thermal input into useful work output, because the second law of thermodynamics mandates that some energy must always be rejected to a cold reservoir to maintain entropy balance. This efficiency ceiling emerges from the statistical mechanical requirement that thermal energy conversions must increase total entropy, forcing every heat engine to dump waste energy into its cold reservoir rather than converting all available thermal input into organized mechanical motion that could perform useful tasks. Real-world engines, like automobile internal combustion systems, steam turbines and jet propulsion mechanisms operate at efficiencies significantly below Carnot limits due to practical constraints including friction losses, incomplete combustion, heat transfer irreversibilities, and material limitations that prevent achievement of theoretical performance boundaries. The thermodynamic impossibility of perfect efficiency stems from the fundamental asymmetry between organized energy forms like mechanical work and disorganized thermal energy, where conversion from order to disorder occurs spontaneously, while the reverse transformation requires sophisticated machinery that inevitably introduces inefficiencies through irreversible processes. However, negative temperature reservoirs completely transform these efficiency calculations by enabling heat engine designs that extract work from both hot and cold thermal reservoirs simultaneously, violating conventional wisdom about unidirectional energy flow while remaining perfectly consistent with energy conservation and statistical mechanical principles governing thermal equilibrium. When the hot reservoir exists at negative absolute temperature, energy spontaneously flows from this exotic thermal source into any positive temperature environment, including the engine's cold reservoir, creating conditions where mechanical work extraction accompanies energy transfer in both directions rather than requiring sacrifice of high-temperature thermal energy. These revolutionary engine concepts achieve work outputs exceeding the energy input from the primary hot reservoir because additional energy extraction occurs from the cold reservoir, which would normally represent a waste heat dump but instead becomes a secondary energy source contributing to total mechanical work production. The mathematical efficiency calculations yield values greater than 100% when work's output surpasses thermal energy input from the hot reservoir alone, though total energy balance remains preserved when accounting for energy extracted from both thermal reservoirs, according to rigorous thermodynamic accounting procedures. Energy conservation continues operating according to established physical laws, because the total energy extracted from both reservoirs exactly equals the mechanical work produced plus any residual thermal energy remaining in the system, maintaining perfect energy bookkeeping while achieving efficiency metrics that exceed classical thermodynamic expectations. This unexpected energy flow pattern occurs because negative temperature reservoirs possess internal energy distributions that favor energy transfer to any positive temperature environment, creating thermodynamic driving forces that operate independently of conventional thermal gradients based on numerical temperature comparisons. The practical implications extend far beyond theoretical curiosity, potentially revolutionizing power generation technology if negative. Temperature reservoirs could be artificially maintained using techniques derived from laboratory demonstrations of exotic quantum states in ultra-cold atomic systems. Such engines might extract useful work from an environmental thermal energy that conventional systems cannot access, effectively harvesting waste heat from industrial processes, geothermal ceaseless sources, or even atmospheric thermal fluctuations that currently represent unutilized energy resources. The fundamental limits of thermodynamics require re-examination when negative temperature reservoirs become experimentally achievable, because classical efficiency bounds assumed thermal reservoirs could only exist at positive absolute temperatures where conventional energy flow patterns determine maximum theoretical performance. These discoveries suggest that thermodynamic principles contain hidden complexities that classical theory failed to anticipate, opening conceptual territories where engineering applications might transcend limitations that seemed eternally fixed by natural law, provided that negative temperature reservoir technology develops beyond current laboratory demonstration phases into practical implementation schemes. Could the exotic quantum states achieved in ultra-cold atomic laboratories somehow mirror the mysterious forces driving our entire universe to expand at an accelerating rate? And might these microscopic negative temperature experiments provide crucial insights into cosmic phenomena operating across distances measured in billions of light years? Dark energy represents one of the most perplexing discoveries in modern cosmology, accounting for approximately 68% of the universe's total energy content, while exhibiting the bizarre property of negative pressure that drives cosmic expansion to accelerate rather than decelerate under gravitational influence as classical physics would predict. Astronomical observations reveal that distant galaxies are moving away from us at increasing velocities, suggesting that some unknown repulsive force overcomes the attractive gravitational effects of all visible matter and counteracts the natural tendency for cosmic expansion to slow down over time. The mathematical description of dark energy requires negative pressure terms in Einstein's field equations, creating cosmological models where empty space itself possesses energy density that generates anti-gravitational effects, pushing cosmic structures apart with ever-increasing vigor, despite the enormous gravitational attraction between galaxies, galaxy clusters, and other massive astronomical objects. These cosmic acceleration phenomena share remarkable mathematical similarities with the negative pressure exhibited by the negative temperature atomic systems, where attractive interactions between particles somehow produce outward pressure against external constraints rather than causing gravitational collapse as conventional physics would anticipate. Laboratory negative temperature states demonstrate how quantum many-body systems can simultaneously experience internal attractive forces while generating external pressure that resists compression, creating mechanical properties that mirror the paradoxical behavior attributed to dark energy throughout cosmic evolution over the past several billion years. The scale connections between atomic and cosmic phenomena suggests that fundamental physics principles operating at quantum mechanical levels might provide analogies for understanding gravitational dynamics governing the largest structures in our observable universe, bridging the gap between microscopic quantum effects and macroscopic spacetime geometry. Negative temperature atomic clouds exhibit equation of state relationships where increasing density decreases pressure, while expansion increases the force exerted against boundaries, precisely matching the pressure-density correlations required for dark energy models that explain accelerating cosmic expansion through anti-gravitational effects. Research teams worldwide have begun exploring these connections by studying how negative temperature systems respond to external perturbations, volume changes, and coupling with conventional positive temperature environments, seeking to identify universal principles that might apply across vastly different physical scales and energy regimes. The potential for using small-scale quantum systems to model cosmic phenomena represents an unprecedented opportunity for advancing our understanding of dark energy through controlled laboratory experiments rather than relying exclusively on astronomical observations that require decades or centuries to accumulate sufficient data for meaningful statistical analysis. These laboratory analogies could provide testable predictions about dark energy behavior, cosmic acceleration timescales, and the ultimate fate of universal expansion by examining how negative temperature states evolve under various boundary conditions and interaction scenarios that can be systematically varied within experimental parameters. Quantum simulation approaches using negative temperature atomic systems might reveal whether dark energy density remains constant throughout cosmic history or evolves according to dynamic equations that couple space-time geometry with quantum field fluctuations in ways that current theoretical frameworks cannot adequately describe. The mathematical formalism describing negative temperature thermodynamics shares deep structural similarities with cosmological equations governing dark energy dynamics, suggesting that advances in laboratory quantum many-body physics could illuminate fundamental questions about the nature of spacetime, vacuum energy, and gravitational dynamics operating throughout cosmic evolution. However, cautious optimism remains appropriate because these connections between atomic physics and cosmology represent early stages of theoretical development, requiring extensive validation through both experimental investigation and mathematical rigor before drawing definitive conclusions about cosmic acceleration mechanisms. The scale differences between laboratory atomic systems and cosmic structures span more than 30 orders of magnitude, making direct extrapolation problematic despite encouraging mathematical parallels that suggest underlying physical connections worthy of continued scientific investigation and theoretical development. Current research focuses on identifying which aspects of negative temperature physics might genuinely correspond to dark energy properties versus superficial mathematical resemblances that could mislead researchers into pursuing unproductive theoretical directions based on incomplete understanding of either quantum many-body dynamics or cosmological phenomena. Nevertheless, the striking similarities between laboratory negative pressure observations and cosmic acceleration requirements provide us compelling motivation for interdisciplinary collaborations between atomic physicists and cosmologists seeking to understand whether quantum mechanical principles discovered through controlled experiments might illuminate some of the deepest mysteries surrounding the structure, evolution, and ultimate destiny of our entire universe. How can atomic systems experiencing mutual attraction maintain structural stability while existing in thermal states that should theoretically represent the ultimate extremes of energetic excitation? And what fundamental quantum mechanical principles prevent these impossible configurations from immediately collapsing into gravitational singularities or dissipating through natural relaxation processes? The remarkable stability of negative temperature systems emerges from quantum pressure effects that operate analogously to degeneracy pressure, preventing white dwarf stars from collapsing under their own gravitational weight, except that uncertainty principles, constraints rather than electron exclusion forces, provide the stabilizing mechanism that counteracts attractive interparticle interactions. When atoms achieve population inversions characteristic of negative absolute temperatures, their momentum distributions become concentrated at the highest allowed energy values within bounded quantum spectra, creating kinetic energy configurations that generate outward pressure through purely quantum mechanical effects related to wave function, delocalization, and position momentum uncertainty relationships. This quantum pressure arises because confining particles to small spatial regions necessarily increases their momentum uncertainty, according to Heisenberg's fundamental limitation on simultaneous position and momentum measurements, forcing high-energy atomic states to resist compression despite experiencing attractive interactions that would normally promote clustering and eventual collapse. The uncertainty principle establishes that reducing particle position spreads automatically increases momentum spreads, creating an effective repulsive force that becomes increasingly powerful as atomic confinement approaches quantum mechanical length scales where wave-like properties dominate over classical particle behavior. Energy barriers protecting negative temperature stability emerge from the discrete nature of quantum states within optical lattice potential, where atoms must overcome specific energy thresholds to transition between different momentum configurations rather than following continuous classical trajectories that would permit gradual energy dissipation through smooth relaxation processes. These barriers create metastable thermal configurations where negative temperature populations remain trapped in local equilibrium states, separated from ground state configurations by energetic gaps that require external perturbations or thermal fluctuations to overcome through stochastic quantum tunneling or phonon-assisted transition mechanisms. The quantum many-body nature of negative temperature systems introduces additional stabilization through collective effects, where individual atomic transitions become suppressed by coherent interactions with neighboring particles, creating cooperative phenomena that resist single-particle relaxation processes and maintain population inversions through emergent many-body correlations. Timescale measurements reveal that carefully isolated negative temperature states can persist for hundreds of milliseconds in laboratory environments, representing thousands of natural atomic oscillation periods during which exotic thermal equilibrium remains stable against environmental perturbations and internal relaxation mechanisms that might restore conventional thermal distributions. These persistence times exceed theoretical predictions based on simple two-level atomic models, suggesting that many-body quantum effects provide additional protection against thermal decay through mechanisms not fully understood within current theoretical frameworks describing ultra-cold quantum gas dynamics. The longevity of negative temperature states depends critically on environmental isolation, because coupling with external thermal reservoirs at positive temperatures drives irreversible energy flow that gradually depletes population inversions through thermal contact with conventional matter phases. Natural limits governing negative temperature stability arise from fundamental thermodynamic requirements that isolated systems must eventually reach thermal equilibrium with their surroundings, meaning that perfect isolation becomes impossible over sufficiently long observation periods, as quantum systems inevitably couple with electromagnetic vacuum fluctuations, gravitational fields, or residual environmental perturbations. Relaxation toward positive temperatures occurs through several competing mechanisms, including spontaneous emission of electromagnetic radiation, collisional redistribution of atomic populations, and quantum tunneling between energy levels that gradually restore conventional Boltzmann distributions where low-energy states become preferentially occupied. The return to normal thermal behavior follows exponential decay patterns characterized by specific timescales determined by system parameters including particle density, interaction strength, confinement geometry, and environmental coupling rates that can be experimentally controlled to extend negative temperature lifetimes. Magnetic field fluctuations, laser intensity noise, and mechanical vibrations all contribute to environmental decoherence that limits practical observation windows for negative temperature phenomena, requiring increasingly sophisticated experimental techniques to achieve longer persistence times suitable for detailed investigation of exotic thermal physics. Understanding these stability mechanisms provides insights into fundamental questions about thermodynamic equilibrium, quantum many-body dynamics, and the relationship between microscopic quantum mechanics and macroscopic thermal behavior in systems operating far from conventional thermal conditions where classical statistical mechanics provides adequate theoretical descriptions. The discovery that impossible thermal states exhibit robust stability over experimentally relevant timescales demonstrates that negative absolute temperatures represent genuine physical phenomena rather than transient artifacts, establishing these exotic thermal regimes as legitimate subjects for continued scientific investigation and potential technological application development. What happens when respected theoretical physicists publish research claiming that decades of experimental observations and theoretical understanding about negative absolute temperatures represent nothing more than mathematical artifacts based on incorrect entropy definitions. And how does the scientific community navigate fundamental disagreements that challenge the validity of established experimental results? In 2013, shortly after the Munich team's groundbreaking demonstration of negative temperatures in atomic motion, Jörn Dunkel and Stefan Hilbert from MIT published a provocative paper in Nature Physics, arguing that all previous claims about negative absolute temperatures violated basic principles of statistical thermodynamics and resulted from using inappropriate entropy formulations that lack mathematical rigor. Their controversial analysis contended that the Boltzmann entropy definition, traditionally employed in negative temperature research, contains fundamental inconsistencies when applied to systems with finite phase space, proposing instead that only the Gibbs entropy formulation provides thermodynamically consistent results for bounded energy systems. According to Dunkel and Hilbert's mathematical analysis, the volume entropy approach developed by Josiah Willard Gibbs in the early 20th century prevents temperature from ever becoming negative because this alternative entropy definition maintains positive values even when energy distributions achieve population inversions that would yield negative temperatures using conventional Boltzmann statistical mechanics. The entropy definition controversy strikes at the mathematical foundation underlying all thermal physics, because temperature emerges directly from the derivative relationship between entropy and energy, meaning that different entropy formulations necessarily produce different temperature calculations for identical physical systems. Boltzmann entropy counts the logarithm of accessible microstates corresponding to specific energy configurations, creating entropy measures that can decrease when energy additions force particles into more constrained high-energy configurations within bounded quantum spectra. Conversely, Gibbs volume entropy integrates over continuous phase space regions, yielding entropy values that always increase with energy regardless of whether systems exhibit population inversions, thereby preventing negative temperature scenarios from arising through pure mathematical construction rather than physical reasoning. Experimental researchers immediately mounted vigorous defenses of negative temperature validity, arguing that laboratory observations provide unambiguous evidence for population inversions and thermal states beyond positive infinity that cannot be dismissed through alternative mathematical definitions that ignore physical reality. Nuclear magnetic resonance experiments spanning 60 years consistently demonstrate negative temperature behavior in spin systems, while ultra-cold atomic experiments reveal momentum distribution inversions that correspond precisely to theoretical predictions based on Boltzmann statistical mechanics applied to bounded energy systems. The experimental community emphasized that physical phenomena should determine appropriate mathematical frameworks rather than allowing abstract mathematical preferences to dictate which experimental observations deserve recognition as genuine thermal physics versus measurement artifacts requiring alternative interpretation. Mathematical consistency arguments became central to the debate because different entropy approaches yield contradictory conclusions about identical experimental data, forcing physicists to confront fundamental questions about which mathematical tools provide correct descriptions of thermal equilibrium in quantum systems with finite energy spectra. Supporters of Gibbs entropy argue that their approach maintains thermodynamic consistency by preventing violations of the second law that might occur if entropy could decrease during energy-adding processes characteristic of negative temperature transitions. However, advocates for Boltzmann entropy contend that population inversions represent genuine thermal equilibrium states where entropy reductions accompany energy increases in physically meaningful ways that reflect the bounded nature of quantum energy spectra rather than mathematical pathologies. The ongoing resolution process exemplifies how science progresses through structured disagreement, where competing theoretical frameworks undergo rigorous testing against experimental evidence, peer review scrutiny, and mathematical analysis aimed at determining which approach provides superior explanatory power and predictive capability. Multiple research groups have conducted independent experiments designed to test specific predictions from both entropy formulations, seeking decisive evidence that could resolve the controversy through empirical data rather than purely theoretical arguments about mathematical consistency or conceptual elegance. The human element in this scientific dispute reveals how personal investment in specific theoretical approaches can influence interpretation of experimental results, requiring the broader physics community to maintain objectivity while evaluating competing claims about fundamental concepts like temperature and entropy. This controversy demonstrates that even seemingly well-established scientific concepts remain subject to re-examination when new theoretical perspectives challenge underlying assumptions, forcing researchers to distinguish between mathematical convenience and physical truth through careful analysis of both experimental evidence and theoretical foundations governing statistical mechanical descriptions of thermal phenomena. How might the discovery of negative absolute temperatures fundamentally reshape our understanding of basic physical concepts that form the bedrock of modern science education? And what revolutionary implications could emerge as quantum technologies exploit these exotic thermal states to achieve computational capabilities beyond anything possible with conventional matter? The existence of genuine negative temperatures forces physicists to reconsider fundamental definitions of thermal equilibrium, energy distribution, and statistical mechanics that have guided scientific thinking for over a century, revealing that temperature represents a more nuanced concept than simple measures of average particle motion or thermal sensation. These discoveries demonstrate that quantum mechanical effects can enable thermal states that appear classically forbidden, showing how microscopic quantum principles create macroscopic phenomena that violate everyday intuitions about hot and cold while remaining perfectly consistent with deeper mathematical structures governing statistical physics. The quantum superposition and entanglement effects underlying negative temperature systems illustrate how collective quantum behavior transcends individual particle properties, creating emergent thermal characteristics that exist only within many body quantum contexts where classical analogies break down completely. Energy distribution patterns in medicine. Negative temperature regimes reveal hidden symmetries in statistical mechanics where population inversions represent mirror images of conventional thermal states, suggesting that thermal physics contains unexplored territories accessible only through quantum engineering techniques that manipulate energy spectra in ways impossible using classical methods. Thermodynamic boundaries established during the 19th century assumed that all physical systems possessed unbounded energy spectra, where particles could achieve arbitrarily high velocities through sufficient heating. But negative temperature discoveries prove that bounded quantum systems follow alternative thermodynamic rules that extend classical laws into previously unexplored parameter regimes. These extensions require new theoretical frameworks capable of describing thermal behavior when energy additions decrease entropy rather than increasing disorder, challenging textbook presentations of the second law and forcing development of more sophisticated understanding about information, energy, and thermal equilibrium relationships. Technological implications span multiple frontier research areas where negative temperature systems could enable unprecedented precision in quantum computing applications, atomic clocks, and quantum sensing devices that exploit population inversions to achieve measurement sensitivities beyond classical limits imposed by thermal noise and environmental fluctuations. Quantum computers might utilize negative temperature states to maintain coherent superposition configurations for extended periods, overcoming decoherence limitations that currently restrict quantum information processing capabilities and preventing achievement of fault-tolerant quantum computation necessary for solving classically intractable mathematical problems. Precision measurement technologies could exploit negative temperature atomic ensembles to create quantum sensors with enhanced sensitivity to gravitational fields, magnetic variations, and electromagnetic radiation, opening applications in fundamental physics research, geological surveys, medical imaging, and navigation systems requiring unprecedented accuracy levels. Educational transformation becomes inevitable, as physics curricula must accommodate discoveries that contradict established teaching methods while maintaining pedagogical clarity about fundamental principles without overwhelming students with mathematical complexity that obscures physical intuition about thermal phenomena. Textbook revisions will need to present temperature as a more sophisticated concept than simple kinetic energy measures, introducing entropy-energy relationships and bounded quantum systems without sacrificing accessibility for undergraduate education while preparing students for advanced research involving exotic quantum states. Teaching laboratories may eventually incorporate negative temperature demonstrations using tabletop atomic physics equipment, allowing students to observe population inversions directly rather than relying on theoretical descriptions of phenomena that seem to violate common sense about thermal behavior. Future experimental investigations will explore whether negative temperatures can be achieved in solid-state systems, molecular ensembles, and engineered metamaterials that provide alternative platforms for studying exotic thermal physics without requiring ultra-cold atomic gas techniques currently necessary for laboratory demonstrations. Next-generation research programs aim to develop negative temperature systems with longer stability times, higher particle numbers, and stronger interactions that could bridge laboratory demonstrations with practical technological applications requiring robust operation under realistic environmental conditions rather than idealized experimental isolation. Interdisciplinary collaborations between atomic physicists, condensed matter researchers, quantumers, information scientists and cosmologists will investigate connections between negative temperature laboratory systems and fundamental questions about dark energy, quantum gravity, and the thermodynamic properties of black holes where conventional thermal physics approaches its conceptual limits. These discoveries ultimately suggest that our current understanding of thermal phenomena represents only the beginning of a much richer theoretical landscape where quantum mechanics enables thermal states that classical physics deemed impossible, promising continued surprises as experimental techniques advance and theoretical frameworks evolve to accommodate increasingly exotic quantum matter phases. What profound lessons about the fundamental nature of reality emerge when scientists discover that the universe operates according to principles so counterintuitive that they challenge our most basic assumptions about how physical systems should behave, and how might these revelations transform our personal relationship with the mysterious cosmos we inhabit? Nature's extraordinary creativity consistently surpasses human imagination by revealing phenomena that seem to violate logical expectations while following mathematical laws of breathtaking elegance and precision, demonstrating that reality operates according to principles far more sophisticated than our evolutionary heritage equipped us to comprehend intuitively. The discovery of negative absolute temperatures exemplifies how physical laws transcend common sense limitations, showing that temperature itself contains hidden depths that remained invisible until quantum mechanics provided mathematical tools capable of describing thermal behavior in previously inaccessible parameter regimes where classical intuitions completely fail. These exotic thermal states demonstrate that nature routinely achieves what appears impossible according to everyday experience, revealing that our sensory perceptions and cognitive biases provide inadequate guidance for understanding the true architecture underlying physical phenomena that govern everything from subatomic particles to cosmic evolution. Dependencies become apparent when examining how different physical principles dominate behavior at microscopic versus macroscopic levels, with quantum mechanical effects enabling thermal states at nanoscale dimensions that would violate thermodynamic laws governing larger systems where statistical averaging smooths away quantum fluctuations and uncertainty effects. The same atoms that obey classical mechanics when forming ordinary matter can achieve negative temperatures when confined within optical lattices operating at quantum scales, illustrating how fundamental physics principles shift dramatically across different size ranges within a single coherent theoretical framework. Molecular behavior follows quantum rules that permit superposition, entanglement, and population inversion effects completely absent from macroscopic thermal experience, where large numbers of particles create statistical regularities that mask underlying quantum strangeness through collective averaging processes. Scientific humility becomes essential when confronting discoveries that reveal how limited our current theoretical understanding remains, despite centuries of accumulated knowledge about thermal physics, statistical mechanics, and quantum behavior that seem to provide comprehensive descriptions of natural phenomena. The negative temperature controversy demonstrates that even fundamental concepts like entropy require ongoing refinement, as experimental techniques reveal new physical regimes where established mathematical formulations may need modification or replacement by more sophisticated theoretical frameworks. Acknowledging these limitations does not diminish scientific achievement, but rather highlights the dynamic nature of scientific progress, where each discovery opens new questions that challenge existing paradigms and force researchers to develop increasingly nuanced understanding of natural complexity. Wonder preservation requires maintaining childlike curiosity and appreciation for mystery, even as scientific knowledge augments, recognizing that deeper understanding often reveals greater rather than lesser complexity in the fundamental structures governing physical reality throughout the observable universe. The mathematical beauty underlying negative temperature physics demonstrates that nature operates according to principles of extraordinary sophistication that inspire awe rather than diminishing mystery, showing how scientific discovery enhances rather than reduces our sense of cosmic wonder. Each answered question about exotic thermal states generates new puzzles about quantum many-body dynamics, thermodynamic foundations, and the relationship between microscopic quantum mechanics and macroscopic thermal behavior that continues expanding the frontier of unknown phenomena, worthy of investigation. Continuing mysteries encompass vast territories of unexplored physics where negative temperatures represent merely one example of exotic phenomena that may exist within parameter regimes currently beyond experimental access or theoretical comprehension, suggesting that numerous additional surprises await future generations of researchers. The connection between negative temperature systems and cosmological dark energy hints at deep relationships between laboratory quantum physics and cosmic evolution that could revolutionize understanding of gravitational dynamics, space-time structure, and the ultimate fate of universal expansion over cosmic timescales. Quantum gravity effects, black hole thermodynamics, and the information paradox represent additional frontiers where conventional physics approaches its conceptual limits, potentially requiring paradigm shifts analogous to the recognition that temperature can exist below absolute zero under appropriate quantum mechanical conditions. Personal reflection on these discoveries can transform how we perceive our place within a universe capable of achievements that exceed human imagination while following mathematical principles accessible through patient scientific investigation and theoretical development. Understanding that reality transcends our intuitive expectations encourages intellectual humility, alongside appreciation for the remarkable human capacity to discover truths about nature through careful experimentation and mathematical analysis that reveals hidden patterns underlying apparent chaos. These insights suggest that maintaining wonder about natural phenomena represents not naive romanticism, but rather appropriate recognition of the profound mysteries that continue surrounding us despite remarkable scientific progress in understanding fundamental physical laws governing everything from quantum mechanics to cosmic evolution. How remarkable that our gentle exploration began with something as familiar as the chill of winter air against your skin, and led us into realms where the fundamental nature of temperature itself reveals secrets that challenge everything we thought we understood about hot and cold throughout the universe. We started our journey in the most ordinary places, remembering those crisp winter mornings when your breath becomes visible clouds of vapor and ice cubes clink against glass surfaces in kitchen refrigerators, experiences so common that they seem unremarkable until we peer beneath their surface simplicity. Those everyday encounters with coldness opened pathways into the invisible world where atoms dance their eternal choreography, moving faster when heated and slowing when cooled, according to patterns that connect your personal thermal sensations with fundamental physical laws governing matter throughout the cosmos. From these familiar beginnings, we ventured toward absolute zero, that theoretical foundation where atomic motion should cease completely, discovering how Lord Kelvin's mathematical extrapolations revealed the existence of a thermal basement below which temperatures cannot descend according to classical physics understanding. The Kelvin scale transformed our perspective by establishing measurement systems that begin from nature's own reference point rather than arbitrary human conventions, revealing that room temperature exists nearly 300 degrees above the cosmic foundation, while stellar cores reach millions of degrees in the opposite direction. We witnessed how modern laboratories push matter to within billions of degrees from absolute stillness, creating conditions where quantum mechanical effects emerge like whispered secrets normally hidden by thermal noise, demonstrating that approaching the ultimate cold reveals new physics rather than simply achieving perfect motionlessness. Through historical discovery, we encountered Edward Purcell and Robert Pound's astonishing 1951 observations at Harvard University, where nuclear magnetic resonance experiments yielded temperature readings that violated every established principle about thermal behavior by displaying negative values on instruments calibrated according to absolute temperature scales. These pioneering researchers found themselves confronting experimental data that suggested certain atomic systems could achieve thermal states below absolute zero, challenging fundamental assumptions about temperature limits while opening entirely new territories for scientific exploration and theoretical development. Nuclear spins behaved like microscopic compass needles that could be flipped between orientational states possessing different energy levels, creating population inversions where more particles occupied high-energy configurations than low-energy alternatives according to quantum statistical distributions that defied classical thermal expectations. The deeper meaning emerged when we discovered that temperature reflects relationships between energy and entropy rather than simple particle velocities, revealing how bounded quantum systems enable thermal states impossible within unlimited classical energy landscapes where particles can achieve arbitrary speeds through sufficient heating processes. Into modern achievement, we explored the groundbreaking 2013 Munich experiments, where Ulrich Schneider, Emanuel Bloch, and their colleagues successfully extended negative temperatures beyond nuclear spins into the actual translational motion of ultra-cold atoms confined within optical lattice structures created by the intersecting laser beams. These researchers demonstrated that kinetic energy itself could achieve population inversions through sophisticated quantum engineering techniques that artificially bounded atomic motion within finite energy ranges analogous to nuclear spin systems, but applicable to particle movement through space. Their experimental recipe combined ultra-cold potassium atoms, optical lattice, confinement and Feshbach resonance interactions to create stable negative temperature states, exhibiting inverted momentum distributions where fast-moving particles outnumbered slow-moving alternatives contrary to all classical thermal intuition. Toward cosmic connections, we explored how negative temperature systems exhibit negative pressure properties remarkably similar to dark energy characteristics that drive accelerating cosmic expansion, suggesting possible links between laboratory quantum physics and cosmological phenomena operating across scales spanning from atomic dimensions to universal structure. These discoveries raised profound questions about whether microscopic negative temperature experiments might illuminate fundamental mysteries about space-time dynamics, gravitational behavior, and the ultimate fate of cosmic evolution through mathematical relationships that bridge quantum mechanics with general relativity. The controversial debates surrounding entropy definitions and experimental interpretation demonstrate how science progresses through structured disagreement where competing theoretical frameworks undergo rigorous testing against empirical evidence and mathematical consistency requirements. Back to wonder, we find ourselves enriched by understanding that transcends simple factual accumulation, gaining appreciation for nature's extraordinary creativity in achieving phenomena that exceed human imagination while following mathematical principles accessible through patient scientific investigation and theoretical development. The mystery persisting at reality's heart reminds us that each answered question generates new puzzles worthy of continued exploration, revealing that scientific knowledge represents an ongoing dialogue with natural complexity, rather than final conquest of cosmic secrets through human intellectual achievement. How do we reconcile the profound discomfort of discovering that nature operates according to principles that contradict our most deeply held intuitions about reality, and what inner transformation occurs when we learn to find peace within the paradoxes that define the frontiers of human knowledge? Accepting paradox becomes a fundamental skill for anyone seeking to understand modern physics, where seemingly contradictory phenomena like negative absolute temperatures coexist with classical thermal behavior within a single coherent theoretical framework that encompasses both familiar and exotic thermal regimes. Science progresses by embracing rather than rejecting apparent contradictions, recognizing that surface-level conflicts often reveal deeper truths about natural complexity that transcends simple either-or categorizations based on everyday experience and common-sense expectations. The ability to hold multiple perspectives simultaneously without demanding immediate resolution reflects scientific maturity that acknowledges partial understanding as a valuable stepping stone toward more complete knowledge, rather than an intellectual failure requiring defensive rationalization or premature theoretical closure. The ongoing quest to understand negative temperature physics continues driving research programs worldwide, where dedicated scientists pursue ever more sophisticated experiments designed to probe the boundaries between classical and quantum thermal behavior, using increasingly powerful laboratory techniques. These researchers work with quiet determination to extend negative temperature systems toward longer stability times, higher particle numbers, and stronger interactions that could eventually bridge current laboratory demonstrations with practical technological applications requiring robust operation under realistic environmental conditions. Graduate students spend years mastering the intricate experimental procedures necessary for creating and maintaining exotic quantum states, developing intuitive understanding of phenomena that initially seem impossible, while contributing incremental advances that collectively push the field toward new discoveries. Practical patience emerges as scientists recognize that fundamental research into seemingly impractical phenomena often yields unexpected applications decades or centuries after initial discovery, following historical patterns where abstract theoretical insights eventually transform everyday life through technological innovations impossible to predict during your early investigative phases. Electromagnetic theory developed by Maxwell appeared purely academic until radio communication revolutionized global society, while quantum mechanics seemed like mathematical curiosity before enabling modern electronics, computing, and medical imaging technologies that define contemporary civilization. Similarly, negative temperature research may eventually enable revolutionary advances in energy conversion, quantum computing, or precision measurement that remain invisible from current perspectives but could reshape human capabilities in ways we cannot yet imagine. Beauty and understanding provide sufficient justification for scientific inquiry independent of practical applications, because discovering fundamental truths about natural behavior satisfies deep human curiosity about our cosmic context and reveals mathematical structures of breathtaking elegance underlying apparent chaos. The mathematical formalism describing negative temperature systems exhibits symmetries and patterns that inspire aesthetic appreciation analogous to great art or music, demonstrating that intellectual beauty represents a legitimate criterion for evaluating scientific theories alongside empirical accuracy and predictive power. Knowledge pursued for its own sake enriches human culture by expanding our conceptual vocabulary for describing reality, providing metaphors and analogies that enhance literature, philosophy, and artistic expression, while deepening our appreciation for natural complexity and mathematical sophistication. Personal takeaway from impossible physics involves developing comfort with mystery and uncertainty as permanent features of existence rather than temporary obstacles requiring immediate resolution through additional research or theoretical development. Understanding that atoms around us constantly participate in quantum mechanical processes that defy classical description transforms ordinary experience by revealing hidden depths within familiar objects and phenomena that seemed completely understood through everyday observation. Sitting in a comfortable room, you can appreciate that the air molecules surrounding you follow statistical distributions, governed by principles sophisticated enough to permit exotic thermal states under appropriate laboratory conditions, connecting your immediate environment with frontier physics through shared mathematical foundations. This awareness doesn't change practical daily activities, but adds layers of meaning and connection that enrich routine experiences with scientific wonder and cosmic perspective that transcends immediate practical concerns. Quiet satisfaction emerges from recognizing that partial understanding represents genuine achievement rather than intellectual inadequacy, because the universe consistently proves more complex and beautiful than any finite human mind could fully comprehend through complete theoretical mastery. Learning to find peace within incomplete knowledge reflects wisdom that accepts natural mystery as intrinsic rather than temporary, appreciating the journey of discovery as valuable independent of reaching final destinations that may remain forever beyond human intellectual grasp. The humility required for living comfortably with impossible physics cultivates character traits that benefit other life domains where certainty proves elusive and simple. Answers fail to capture nuanced realities requiring patient observation, careful reasoning, and acceptance of ambiguity as fundamental, rather than problematic aspects of authentic engagement with complex systems. What gentle wisdom emerges from our shared journey into realms where temperature itself transcends the boundaries we once thought absolute? And how might this exploration continue resonating within your thoughts long after our conversation ends tonight? Rather than seeking dramatic revelations or earth-shattering conclusions, we find ourselves arriving at a place of quiet appreciation for the remarkable subtlety underlying phenomena that initially appeared to violate fundamental laws governing thermal behavior throughout the natural world. Our exploration revealed how scientific understanding evolves through patient observation, careful experimentation, and theoretical refinement that gradually unveils hidden complexities within concepts as seemingly straightforward as hot and cold. The discovery that atoms can achieve temperatures below absolute zero demonstrates nature's capacities for surprises that humble human assumptions while inspiring continued investigation into mysteries that remain tantalizingly beyond current theoretical grasp. These negative temperature states remind us that reality consistently exceeds our intuitive expectations, operating according to mathematical principles elegant enough to accommodate apparent paradoxes within coherent frameworks that unify seemingly contradictory phenomena. From winter mornings and ice cubes to exotic quantum gases exhibiting population inversions, we traced connections spanning everyday experience to frontier laboratory research, where dedicated scientists create conditions that exist nowhere naturally within the observable universe. The historical progression from Lord Kelvin's theoretical insights through Purcell and Pound's nuclear spin discoveries to modern ultra-cold atomic experiments illustrates how scientific knowledge builds incrementally across generations of researchers who contribute pieces to puzzles, whose complete solutions may require centuries of collaborative effort. Looking forward, countless questions await future investigation as experimental techniques advance and theoretical understanding deepens through continued dialogue between theory and observation that drives scientific progress toward ever more sophisticated appreciation of natural complexity. Will negative temperature systems eventually enable revolutionary technologies that transform energy conversion, quantum computation, or precision measurement beyond current imagination? How might connections between laboratory negative temperature physics and cosmological dark energy illuminate fundamental questions about space-time structure, gravitational dynamics, and universal evolution? These mysteries invite continued curiosity from anyone willing to maintain wonder about phenomena that challenge comfortable assumptions about how physical reality should behave according to everyday experience and conventional wisdom. The privilege of exploring these ideas together reflects the remarkable human capacity for intellectual adventure that transcends immediate practical concerns, demonstrating how curiosity about abstract scientific concepts can provide profound satisfaction independent of utilitarian applications or material benefits. Sharing this journey through the landscape of impossible temperatures creates connections between minds seeking understanding of natural phenomena that operate according to principles more sophisticated than any single human perspective could encompass through individual effort alone. The collaborative nature of scientific discovery extends beyond professional researchers to include anyone willing to engage thoughtfully with ideas that expand conceptual horizons and deepen appreciation for cosmic complexity revealed through patient investigation and mathematical analysis. If tonight's gentle exploration of negative absolute temperature physics has enriched your understanding, sparked new questions, or simply provided peaceful contemplation about the mysterious universe we inhabit, your continued engagement through subscriptions, thoughtful comments, and sharing with others who might appreciate such intellectual adventures would mean more than words can adequately express. These conversations thrive through community participation that brings diverse perspectives to bear on scientific concepts, creating dialogue that enhances everyone's appreciation for natural phenomena while building bridges between specialized research and broader public understanding of discoveries that illuminate fundamental aspects of physical reality. The universe continues revealing capabilities that exceed our imagination, consistently demonstrating that each answered question opens pathways toward new mysteries worthy of lifelong investigation by anyone maintaining childlike curiosity about how things work at the deepest levels accessible through scientific inquiry. Negative temperature physics represents just one example of exotic phenomena, awaiting discovery as experimental techniques advance and theoretical frameworks evolve to accommodate increasingly subtle aspects of quantum mechanical behavior in extreme parameter regimes. The mathematical beauty underlying these discoveries suggests that nature operates according to principles far more sophisticated than everyday experience would suggest, inspiring continued investigation into relationships between energy, entropy, information, and consciousness that may ultimately transform our understanding of what it means to exist within this remarkable cosmos. Until we explore together again in future conversations that venture into other territories where scientific discovery challenges conventional wisdom while revealing hidden depths within familiar phenomena, may your curiosity remain alive to the countless wonders surrounding us at every scale, from subatomic particles to galactic clusters, all governed by laws whose complete understanding remains an open invitation for continued learning and appreciation throughout our brief but remarkable journey through space-time itself.